Okay, welcome everybody to my presentation, AI-driven data analysis for marketing decisions. My name is Professor Dr. Hannes Antonschmidt, and I'm from SRH University of Applied Sciences in Berlin. Yeah, what do I want to show you today is a brief overview about how AI can be used for marketing purposes, and then a demonstration how you can use this concretely with your own data, and this is based on a study that I recently published. Yeah, as a start, when most marketing practitioners analyze data, they tend to seek for linear trends, linear relationships. That is sometimes the case that the relationships are indeed linear, and then obviously these standard methods are most powerful. However, I want to show you that when we are dealing with nonlinear relationships, we can make our life easy by using AI and let AI find a function instead of ourselves trying to find a trend that potentially fits the data. When we speak about AI and machine learning, we should differentiate between two approaches, which are supervised and unsupervised learning. Yeah? In both cases, we want to come up with an algorithm that eventually is able to classify our data, to predict trends, etc. But in the supervised learning case, we supply the algorithm with training data that serves as experience. And then the algorithm is optimized based on its training and can then independently categorize raw data and come up with classifications, with predictions, etc. In an unsupervised learning environment, we have just the data, and we start with the data, and the algorithm then learns from the data. It independently identifies patterns, structures, regularities, categories, etc. And then, based on this, it again comes out with an output, classification, prediction, etc. Now, what are the advantages of using AI for data analysis? So, what are the advantages for letting a computer find the trend in the data, either with previous learning or even independently? We are more flexible in dealing with nonlinear and irregular data structures. There's very few restrictions on the input data. We can handle a very large number of features, so very large number of, if you like, independent variables. These methods are also insensitive to multicollinearity, so insensitive towards relationships between independent variables. And we do not need a hypothesis between the relationship between predictors and outcomes a priori. So we don't need to hypothesize any relationship beforehand. We can just let it go and find a trend which we previously may not even have imagined. And frequent or many companies already use these characteristics of artificial intelligence for marketing purposes. You see here that is a company called Akio, and they offer that you can use their services for various marketing purposes. So you can use their prediction models for augmented lead scoring, so knowing how likely it is that a lead will be converted. You can predict the customer lifetime value. You can predict the likelihood for renewals. You can optimize your content, you know where to show it, that it reaches the optimal target group, etc., etc. So many use cases already now exist, and many companies already exist that offer their services. And when you want to use it, you again have to supply them with training data. So they are using supervised learning. That means you have to supply them with training input data. Then the program automatically develops a model for you and predicts whatever you want to have predicted. Yeah. Here in this case, the company wanted a prediction about the sales, and it wanted to know which of these different marketing channels is most influential in terms of sales. And it's easily shown that TV is the most effective channel. Yeah. So it makes your life very easy. Uploading training data, then the model is developed by this company, and then you get the result and can easily interpret the result. In the following, I want to demonstrate now what you have to do until you can come up with these results, or what you can do if you want to develop your own model. And I want to demonstrate this with a study that I recently published, where we indeed used a data set and we had it analyzed with a machine learning approach, support vector machine model in this case. So we had overall a big data set of 6,500 observations, and we had 78 features, so 78, if you like, independent variables. So sufficiently large, sufficiently complex data set, and this is also a requirement when you want to use it for machine learning. It should obviously to be applicable or to have any added value. It is rather for the big data sets, for the complex data sets. Now, we need to define an outcome variable, or I termed it here dependent variable. That means we need something that we want to predict, because in this case we want to use the algorithm. We want to develop an algorithm for prediction. It's prediction if someone wants to buy a particular product. In this case, it was a product bundle. You see here this product bundle, and we wanted to know we wanted the algorithm to predict the buying behavior of the people, to correctly predict, will someone now choose this option or will they choose another option? So what do we need? Again, in this case, supervised learning, we need training data. And the training data set was basically an Excel table where we had stored all our survey data. These independent variables are called features in the machine learning realm. And then we need also one target or response variable, one outcome variable. In this case, has the product been chosen, then it's 1. And if the product has not been chosen, then it's 0. And now, up until here, this is pretty much the same as with any linear model. However, when we go to machine learning and support vector machines, it's important that we can interpret every row, so every respondent, as a vector in a multi-dimensional feature space. So every respondent is equal to one vector, in our case, in a initially 78-dimensional feature space. Fairly complex, fairly hard to imagine, but this is what we need to understand also the difference between the linear model and the support vector machine model. Now, we want to know, obviously, which factors now differentiate travelers who choose the sustainable option from travelers who do not choose the sustainable option. And we applied, as I said, a support vector machine. Here is a brief glimpse into the technical procedure. So we obviously have two data groups, and we want to maximize the difference between these data groups. We want to find a hyperplane that maximizes the differences between groups. Here it's pretty simple because it's just 2 dimension, but now imagine if the data has 78 dimensions. Obviously the data is pretty mixed, and so it's quite tough, which is why we need the computer power to find this separating hyperplane. What we need, and also what you would practically need if you want to apply a supervised machine learning approach, you need a balanced data set. So a data set that has the same number of positive and negative cases. So people who choose a product and people who do not choose our product. And then we divide this data set into a training set and a test set, both roughly the same size, so both roughly 50% of this original data set. Then we use the training set to feed into our model, to train our model for model development. Yeah. And then we test the model that has been trained on the training set. We test it on the remaining 50% on the test set. Yeah. To see how good is it now in terms of predicting that someone will choose our product or not. So what happens practically is that you choose, well, it's pretty technical here, but you choose a kernel function that transforms your data. Then we have a linear model in feature space that only uses the kernel inner products. We predict via a kernel expansion, and importantly, the fourth point, the decision function in input space is nonlinear. So we eventually, this whole procedure leads up to a very complex function that is nonlinear for us in the input space. Luckily, obviously, the computer uses this for the prediction. We don't have to calculate anything by hand, but just to let you know how the procedure eventually works and how we come up with our nonlinear decision function at the end of the day. More important for practitioners is certainly the results that you eventually get. Usually, and this is also the case in many prediction applications for these companies that I've shown you, these online tools that I've shown you, the results come in the form of a contingency table. A contingency table compares the predicted class with the observed class. Yeah. So we predicted either less sustainable consumer or sustainable consumer. So sustainable consumer chooses the sustainable product. Less sustainable consumer does not choose it. And then we have the actual outcome, the actual observed class. It could be a less sustainable consumer or a sustainable consumer. Now, decisive for the quality of our model is obviously the diagonal, where observed class and predicted class match. Yeah. So in 386 cases, we have predicted less sustainable consumer, while it was actually a less sustainable consumer. And in 354 cases, we have predicted sustainable consumer, where it was indeed a sustainable consumer. Anything off the diagonal, we were wrong. Yeah? We predicted less sustainable consumer, while it was a sustainable consumer, or we predicted sustainable consumer, while in fact it was a less sustainable consumer. So obviously the higher the number in the diagonal versus the off diagonal, the better the prediction quality. Yeah. Now, when our model was used on the training data, in the training environment, it classified 72.1% of these known cases correctly. Okay, it works in the training environment reasonably well, but as I said before, it has to be validated on the test set. So obviously, to test a model on the test set is more challenging because this is for the model new data. It has a previous knowledge, but still the test set is somewhat new data. And so the next contingency table, when we apply it on the test set, is even more informative. And once more, we have the diagonal, and we see the prediction performance is still reasonable with 70.6% of correct classifications of unknown cases. Now, when you use machine learning or any artificial intelligence model for prediction, you also should observe the model performance and interpret it correctly. Obviously, prognosis accuracy of 70.6% is not ideal. still is reasonable. So for practical use, you may decide, okay, I can use it because it's, as you see, it's better than proportional chance criterion. Or you may say, I still have to train it further. I have to use even more training data, maybe change the composition of features and get an even higher prognosis accuracy. Then you should also observe the sensitivity and the specificity. Sensitivity would be the accuracy in identifying positive cases, so in our case buyers, versus specificity, which would be the accuracy in identifying negative cases, in our case non-buyers. Yeah? Here in this case it's quite okay because sensitivity and specificity do not fall apart largely. They are pretty much the same. So the model is good in identifying positive cases and good in identifying negative cases. If it falls apart too much, you may again use more training data, change the composition of features, etc. Now, obviously, it's important not just to use the model for prediction and to say, okay, I have an outcome here, I can predict an outcome, but I also want to know what now caused the outcome, what now causes someone to choose our product. This is obviously for marketing practitioners very important to know which variables can I manipulate, where can I step in, what can I do to increase also the likelihood of buying. And this is not so straightforward as with linear models, where you have beta parameters, where you can easily say, every 1 unit change leads to, or every variable has a particular impact based on the beta parameter. Here we have the vector weight as a heuristic instead of a beta parameter, where we say each change in 1 unit in 1 variable leads to a particular change in the outcome variable. Here we have a different statistics that measures the influence of a single feature on the discrimination between the classes. It's not interpretable in the same way as the beta parameters, but still you can rank these features according to their importance in terms of categorization. So in this case, we see eating organic food is important to me is by far the most influential in terms of the discrimination function. And this is also important for marketing practitioners. Which of your features are now most influential in terms of someone buying or not buying your product? In this case, we could say, we could probably highlight the organic qualities of the product. It's a food product, so organic quality of the food product should be highlighted to increase the selling potential. So concluding what I've shown you in a very, very brief way, obviously there's much more to know about it, much more to discover about it, but marketing data can conveniently be used to generate new insights. AI tools greatly increase the possibilities for data analysis. So you can confidently use AI on your existing marketing data, maybe even the data that you used to find linear relationships. You can now reuse it and feed it into AI and get even better insights. It's key, though, that you have sufficient training data and also continuously train your models. Again, based on the prediction accuracy, if it's not ideal, you may want to feed in even more training data, at least for supervised learning. And then the output